Hello everyone, this is Vahe with a short video on experiment number 10x, the operational amplifier circuits. So as with the previous labs, this is going to be done using LTspice, and I'm going to give you the report template as usual, so many things are going to be pretty much the same. So basically, in this experiment, we're going to be working with two circuits, and I believe this is going to be a very straightforward experiment as before. So the first circuit is going to be the non-inverting amplifier that we've seen, and the second is the inverting amplifier, and I'm going to show you what you need to do for each one. It's actually very straightforward. I believe you can finish the whole thing in probably an hour of time. Although we can do a lot more with it, but this will give you a feel for how we set things up, how we analyze things, etc. So just to show you how the experiment report template looks like. Okay, so name, UI, and lab section is before, right? And it's got a part. The first part is about the non-inverting amplifier. Again, it'll start with asking you to start with the sample non-inverting amplifier for LTspice first, and it's got a bunch of cases. It'll say, let R1 equal to 1K, R2 equal to 3K. So you have to go to the sample file that I send you and plug in those values, run the simulation, insert the schematic as it shows right here, insert schematic, insert the waveforms, and then ask or answer the question that's asked, which is, was the output voltage clipped? We talked about clipping of the output voltage. Second case, make the R2 5K, the whole thing over again. Case 3, another set of R1, R2, right? Over and over again in R4. So there's 4 cases of 4 different values of R2. We keep R1 the same, we change R2, and then finally it asks, okay, let R1 equal to 1K. Determine the highest value of R2 that will result in the highest gain magnitude without getting the clipping, right? Because as you increase R2, what you'll see is at some point you get clipping. So the question is, which value of R2 will result in no clipping, but as high as possible on the output voltage magnitude, right? So it'll be some number in the range of numbers that we found. I'll let you figure that one out. And then for the next set, we repeat basically the same thing for the inverting amplifier. So there's a little typo here. It should say start with the sample inverting amplifier LTspice file, and I'll show you those in a second. But that's how it's going to look like. Inverting amplifier, you start with the file I send you, you put in the R1s, R2s, run the simulations, and observe what's happening, comment on what's happening, etc., right? So just use these values, and at the end it's going to ask you the same thing. What is the highest value of R2 that you can have without getting the that clipping? All right. So with that said, this is how the template will look like. Let's see how the circuits look like. So the circuit for the non-inverting amplifier for first set of the simulations looks like this. Okay, and if you notice that this is actually a non-inverting amplifier, right? Notice that the input is applied to the positive terminal, and there's feedback through R2 and R1, right? And I showed you that there's 2 ways of drawing a non-inverting amplifier, and I said they were the same. If you look back at the lecture, you'll see that. Okay. So what we have here, we have R2 and R1. The gain is 1 plus R2 over R1. And on the right, I show you how we set up the 9 volts and minus 9 volts for a power supply for the OpAmp, right? Without the power supply, the OpAmp won't work. The OpAmp that we're using is called LT1001. It's very similar to the LM741 OpAmp. So it's a garden variety OpAmp. And the input voltage in this case is a sine wave. It's a 1 volt, 1 kilohertz sine wave. So it's got a period of 1 millisecond. 1 kilohertz means 1,000 cycles per second. So each cycle or each period is 1 millisecond. And the 1 volt means it goes up to 1 volt and minus 1 volt. So for the duration of the simulation, you do not have to change that function generator. And the reason I put function generator is because if we were in the lab, right, we were building this in the lab, you would replace that by our function generator on the benchtop. Similarly, on the right side, I show you plus minus 9 volts. If you look back at the lectures, I told you why we pick it that way, and the middle point is ground, if you notice, right? So we're in the lab, you would set this up using the dual DC power supply, and etc. So that's why they're marked that way, just to let you know that this is actually just one step away from the benchtop work, okay? So what does this setup do? Well, in this simulation, if you look at the right lower side, it says dot trend 3 milliseconds. That will simulate this circuit for 3 milliseconds. So each cycle being 1 millisecond, that's 3 periods, okay? And for the duration of the simulations, both for this amplifier, non-inverting, and the next one, which is the inverting, we do not change the function generator settings, 1 volt, 1 kilohertz, okay? Nor do we change the duration of the simulation. The only thing we will really change is R2, okay? We just have to change the value of R2 over and over again, run the simulation for the 4 cases. The 5th case says, choose the highest value of R2 without getting to the limit. That's what it's all about, okay? But on your own, you can try to change the other things too and just experiment with it, and you can learn a lot with this. The thing that the extra resistor that you see here shown as RL is not necessary, but I just put there as an extra resistor to show you that OpAmp outputs are usually not like what we've been showing them. You could actually put a resistor there, but that resistance RL will not change the value of V out. So I can remove RL if I want to, but typically there might be something there, okay? So that's not going to change our results. And as shown, this being a non-inverting amp, the gain V out over V in is going to be 1 plus R2 over R1. So this is actually ready to simulate, and I'll give you this circuit, okay? Along with this circuit, so this circuit is called non-inverting.asc. I'll also give you the .plt file that goes along with this. So when you put those files together and put them in the same directory as we've been always doing, and just hit the running man, you'll get the simulation results right away. So you don't have to even probe the output voltage. It's that easy, okay? And what do we see here? We see the input and the output. The blue is the input, right? That's the 1 volt height. So let me make this larger so you can see it. So that blue waveform is a 1 volt sine wave, and you see 3 cycles. And the green or yellow or whatever that color is, that's the output waveform, and you can see the amplitude to be 3. Why? Because the gain is 3, isn't it? Because it's 1 plus R2 over R1. R2 was 2K and R1 was 1K. All right? So I can go and, change this around, make this maybe, you just right click on it, right? Right click on the 2K and then enter a new value, right? So let's make this, 2.5K, right? 2.5K. Now the gain is 1 plus 2.5 over 1, 3.5. The gain is 3.1, okay? So then rerun the simulation and see that output jumped up to 3.5. Okay, great. All right, so that's how you're gonna do things. You're just gonna change R2, run the simulation, right? And then, copy both the schematic file and the waveforms to show us that you've done the work. Very simple, as before, right? And I hope you guys know how to copy and paste, right? You just see there are 2 windows, right? You can highlight 1 or 2 of the windows. So you can highlight this window, for example. Let's say Tools, copy bitmap to clipboard, right? And then you open your Word file, and then, and then you say, for example, paste, right? I'm just kind of doing this. It's not this exact question, but you just say paste, right? And there it is. And then you can go on it and make it, maybe a little smaller, right, or something, as you like. Waveform, same thing. I'm just showing it to you once just to remind you. You just go on the waveform like this, or if it's full like that, doesn't matter, right? You go to Tools, copy bitmap to clipboard, right? Then you go to Word and just say paste, right? And then when you're here, it's up to you. You can leave it like that. You can move things around. It says LTspice waveforms here. Maybe do Control Enter for it to move it to the next page or something like that, or keep pushing Enter until it looks good. It's up to you how you want to make it look like, but copy and paste works that way, and you just do it as many times as necessary. Save it, upload it, done. Okay, it's that easy, guys. And I mean, most of you have been doing it, so I don't have to repeat this, but I'm just reminding you in case you forgot, because there might be a lot of things on your mind. Okay, so what else can we do with this? Well, how do we show clipping, right? Well, you'll see as we increase the R2 while keeping R1 the same, the gain is going to increase, right? So the number that we're multiplying the input V in by is going to go higher, and the output voltage obviously is going to go higher. But remember, the output voltage can't really go all the way up to the power supply voltages, right? It cannot go beyond the power supply voltages. Here the power supply voltages are 9 and minus 9. It turns out that, for practical circuits, that we can't even get to 9 and down to minus 9. We're going to be lower than that, okay? Going to be around the 8 volt range, 8 volts minus 8 volts. Let's see how what that happens here. So let me just put in some value here. Let me just put in 12K, okay? 12K, that will make the gain 13, right? 1 plus 12. So run the simulation, and all of a sudden it gets a haircut, right? So you got clipped, is what happened. What's that clipping voltage, right? What's that maximum? Looks to be about 8, and then down to minus 8. Okay, you wanna get a better idea? Well, you go on the waveform, right? You click on the waveform window, you highlight it, and then when the cursor turns across, left click and choose the rectangular area, and then let go, and then you can see you can zoom in more and more and more like this, and you can see that it's about probably 8.0 something volts. If you're not sure, you can just take your cursor and just place it. I'm not putting the left mouse button. I'm just kind of moving the cursor over to this area and place it at that level, and look to the lower left. It says Y equals 8.019 volts. About 8.02 volts is where the plus side is at, as far as the max is concerned. And then if we zoom out and go to the bottom and do the same thing, right? How about over here? Well, somewhere around 8.02 volts, negative 8.02 volts here as well. So that's what we're getting. Okay, so we get a haircut, right? So somewhere between it being 2K and 12K, you get into this region where you get a haircut, okay? So the question is, how high can I make R2 without seeing this clipping? That's the question that's being asked in, I believe, case number 5. So if you go to the template here, right? So you have these cases, right? And I didn't do the case for 3K. I did it for 2.5K. So I should really remove these, right? But nevertheless, there are these cases that are being shown. Case 1, case 2, case 3, case 4. In case 5, there's a question. It says, determine the highest value of R2 that will result in the highest gain magnitude, right? Without showing any clipping. So what you should do is, where the clipping happens from observing case 1 to case 4. So just go to your simulation and start increasing R2 until you just start seeing a little bit of a haircut, and back up a little bit, and then just say approximately R2 equals such and such ohms is that value. Okay, and then take a picture of the schematics, results. You've done the work for the non-inverting amplifier. Okay, and we are basically going to repeat the same thing for the inverting amplifier. So let me show you that, okay? So the inverting amplifier is sitting over here. Let me get that for you. Here's the inverting amplifier. The gain here is minus R2 over R1, right? And again, the setup is exactly the same, except that the input is now being applied to the negative terminal through resistor R1, right? This is the structure for the inverting amplifier. Everything else, the sine wave amplitude, the transient simulation duration, everything is the same. And then R1 and R2 are 1K, 2K as shown. run the simulation, okay, and with the PLT file in place, this pops up. And does this make sense? Yeah, it makes sense because the gain is minus R2 over R1, which in this case is minus 2, right? So you can see that the magnitude of the output is at 2 minus 2. So the gain magnitude, absolute value is 2, right? The R2 over R1 is 2. The negative sign just tells you there's an inversion of phase, right? So if you put in the green sine wave, you get a minus sign. Minus sign meaning minus sin, minus sine wave function, right? So when green goes up, blue goes down first. But as far as the amplitude is concerned, you know, the same way, you can keep increasing this R2 value, and you'll get higher and higher and higher amplitudes, right? Higher and higher magnitudes of the output. But at a certain point, you get clipping. Like for example, let's say I put in, I don't know, 20K, right? I'm just arbitrarily picking 20K. Okay, so here's 20K. Well, so what's the gain? Well, the gain is minus 20, right? The absolute value of that is 20. So my output should be 20 times the input. Input is 1 volt. So do I get a 20 volt sine wave at the output with the inversion, the phase inversion, 180 degrees? Do I get that? No, of course not. I get clipped again, right? I get clipped at those power supply limits minus a volt, right? Theoretically, it should be 9 and minus 9, but practically in real circuits, that output limitation is 1 volt lower than the 9. So in this case, it will be minus 8 plus 8, as shown. So the question is, how high could I have picked R2 without seeing clipping? So, you know, basically 20K is too high. Okay? 20K is too high. So you should go lower and lower and lower until you stop seeing the clipping. And I'm sure you could figure this one out too. So this is basically it for the setups. And so if you know how to work with these, really, you can set up any OpAmp circuit and work with any OpAmp structures like this. All right. So I think that's pretty much all I have to say about this. I'm going to send you a number of things. Okay, so first of all, I'm going to send you this file, right? So I'll show you. I'm going to send you this file, and I'm going to also send you not that file over there, but let's see. I'm going to send you this file, right? So this is the non-inverting, this is the inverting. You'll get these two files on Blackboard. Plus, you'll get the two .plt files that correspond to these, so that you can just go and hit it, then run the simulation, and you get the waveforms right away. On the other hand, if you just run the simulation, and you can go just probe, right? You can just take the probe and connect it to, hit in and out, you know, point to the in and out, and you can get the waveforms that way too. You've done that before, but this way it's easier. And then simply, I'll send you the template and just fill out the template. You know what to do from last one. Just follow directions and answer the simple question. And that will be it. And then you upload it, and that will be the last lab. So I'm going to stop here, upload this to YouTube. So if you're watching this on YouTube, please like and subscribe. And go to my Patreon page. No, I don't have a Patreon page. Just watch this. But I think if you've been doing the previous ones, I'm repeating a lot of things which I should not. You could have probably done this without watching the video. But just to let you know what I'm going to ask, this is basically it. Okay, guys. Thanks very much. Thanks for your patience. And with that, I'm going to stop. And then if there are any questions, of course, you can always post on Piazza. Thank you.